Today I'm going to be talking about ASML and how it is a company that is strengthening its moat in an essential global industry. The traditional disclaimer slide, which basically says that information presented here is as accurate as possible and that investing is on your own risk. So let's get into it. So ASML, it actually has a dual listing. It's listed in the US and in Europe. My recommendation is long. It's currently trading at a price of 680 euros per share with a market cap of 270 billion. In terms of valuation, this year it's currently at 32 times price earnings and a free cash flow yield of 3%. But given the quality of the business, the backlog, and the control of supply that ASML has, I'm pretty comfortable underwriting 2030 metrics, which are a bit more reasonable at 16 times earnings and a 6% free cash flow yield. So in the next 14 slides, I will explain why I think ASML is a wide moat business and a long-term holding. So here are the talking points that I'm going to address, which I think is a good way to put the proper context. I'm first going to be explaining why ASML exists. Then I'm going to be talking about the attractiveness of the semiconductor equipment industry. Then I will talk about the two different machines that ASML sells, which is DUV and EUV. As well, ASML has been able to develop their maintenance and repair business that feeds into the new equipment business that they have, which is very lucrative. How I want ASML to continue to reinvest back into the business at very attractive rates. Then I'll talk about management and how we are aligned with them in terms of compensation. Then finally, valuation, and then risks and pre-mortem, which is something that the pre-mortem is something that we love to do here at Kuwait Capital for each stock page. So how does ASML's IP help the world? So ASML basically exists to provide the machinery, the hardware, to make the fastest, smallest chips at the most efficient cost possible. And they use this technology called lithography, which is actually the most used technology today to make chips. And why is this? Because lithography is the only technology that can reach the level of precision and accuracy necessary for today's smaller, higher density chips. It is a technology with fewer process steps, shorter cycle time, lower cost, and better yield. Lithography is essentially a projection system, and just to provide a bit more background on this technology. So this projection system uses a light that is projected through a blueprint of the pattern that will be printed on the wafer. With the pattern encoded in the light, the system's optics shrink this and focus the pattern onto a photosensitive silicon wafer. After the pattern is printed, the system moves the wafer slightly and prints another copy, rinse and repeat. So these advanced machines can produce a bit more than 300 wafers per hour, which is an impressive level of productivity. And just to give a bit of a background, this is the beginning of the presentation, how chips are made. So basically, these prints are done through transistors, which are printed into a wafer layer after layer, much like the floors of a building, for example, that they kind of build on top of each other. The lowest layers, which are the first ones, are the more dense, and the higher you go on the stack, the more basic the layers. So in this case, a semiconductor manufacturer, which are the clients of ASML, can actually use EUV for the most dense and smaller chips, which are at the bottom, and DUV, which is another machine, for the top layers. And we'll get into this in a bit. But this is a good segue to explain the basic differences between DUV and EUV, which are basically the two machines that ASML sells. DUV stands for deep ultraviolet, and EUV stands for extreme ultraviolet machines. So DUV basically uses a light wavelength of 193 nanometers, and this defines how much resolution they can print on the wafers. So the higher the light wavelength, the lower the resolution. The evolution of this machine is EUV, which ASML has been able to develop the light source at a wavelength of 13.5 nanometers, which is the level at which the light is best reflected off specialized mirrors. This increase in EUV's resolution for chips allows it to make 2 nanometer resolution chips, which are basically the smallest, most perfect chips that exist today in the world. So making chips at scale is one of the most complex processes on Earth. It involves 1,000 single process steps and 100 lithography steps, which is amazing. So basically, EUV lowers the wavelength to improve the printing resolution with the help from special enhancements such as a vacuum and mirror-only optics inside the machines. And as you well know, these chips are in every part of our lives, right? They're in our phones, our computers, data centers, AI, which is hype right now. Uh, Most probably the chips in your cell phone are made with an ASML machine. And here you can see, I hope you guys can see my cursor, but this is kind of like an inside look of one of ASML's machines. If you can see here the purple light, it's basically the ultraviolet light that is being reflected from or against the different mirrors, and they eventually reach down here to print on this basically wafer. And these small boxes that you can see here are actually the chips that go into all of these electronic devices. So with that backdrop, let me continue with this amazing story and amazing business. But before we do that, I'd like to also put a backdrop on what type of industry we're in, kind of like a taking a step back, right? So I did a basic Porter's five forces analysis. And here we are within the semiconductor equipment industry, which has very unique benefits. So I'm going to start with the top one, which threat of new entrants. It's quite low. The amount of innovation that's happened in this industry, especially through ASML, is frankly amazing and creates these high barriers to entry for any type of new entrants, whether it's new technologies or regional players. And ASML is the sole maker of EUVs in the world and has actually been that for almost 15 years now. To the right, we have clients' bargaining power, which I measure as low to mid. On the one hand, clients need these machines. So the clients of ASML, the three main clients are TSMC, Intel, and Samsung. And they also have a couple more second tier clients such as Micron and SK Hynix. So all of these companies are in the business of making the chips, and they use ASML's machines to make these chips in a more efficient manner, smaller, more dense, and faster. So in order for these companies to remain competitive, they need these ASML machines. On the other hand, there's a very high customer concentration. Approximately 60% of ASML's revenues come from the three largest semiconductor manufacturers. So, you know, in this case, this high customer concentration doesn't really give so much pricing power for ASML, and ASML has to balance the relationship with their clients and also, you know, increase prices on a normalized rate. But I wouldn't say that ASML has a very clear pricing power, and it's not really part of the thesis. On the bottom, we have the threat of substitutes, which I also measure as low. The lithography chip making technology continues to be the most efficient method out there, even after several attempts from other competitors or new entrants that are trying new technologies to make these chips in the most efficient manner. But frankly, lithography continues to have the highest market share, and this industry continues to invest in innovation to keep it that way. On the left, the supplier's bargaining power. I think this is the most relevant force in this industry, and I do think that the suppliers have high bargaining power to mid. And let me talk about this a bit more. So ASML needs very reliable suppliers to make high quality niche parts for all their machines. ASML today actually outsources 80% of the parts needed for a machine, which is a lot. And ASML actually decided to outsource their suppliers several years ago to incentivize innovation and competition. And throughout ASML's history, they have acquired very few suppliers in order to bring them in-house. But to this day, they continue to be extremely outsourced. So uh, ASML relies on these suppliers a lot, and therefore I believe that they have high bargaining power. On the other hand, ASML has also signed exclusive agreements with their key suppliers in order for ASML to be their only clients, right? So ASML, when ASML makes an order, they send this certain specifications and also tell them when they need the parts. So, I think it's a balancing relationship, obviously, but I do think it tilts more toward uh, bargaining power for the suppliers. And then finally, in the center, the rivalry amongst competitors, I measure as low. There's no competition in EUV, as ASML is the sole provider of this technology. There's very limited competition in DUV. The other two competitors here are Canon and Nikon, and in total, they both have 6% market share, while ASML has 94% of the DUV market share. So very little competition there as well. And ASML's brand is synonymous to quality, reliability, and trust, which they've been building for the last 30 years. And it's very difficult to beat that. So, in conclusion, this is a great industry to fish in. Going back to ASML specifically, I'd like to talk about how their revenue is composed. ASML continues to be an original equipment manufacturer with good geography diversification and leaning more toward logic chips, which are the most advanced chips. If you can see this first graph, 76% continues to be the selling of their new equipments, which is normal for a company in this industry as they're ramping up the install base of these lithography machines. And 24% is maintenance and upgrade, and basically the service business that ASML also provides, which, as we all know, is a very attractive business model and complements the new equipment segment. On the bottom, the revenue by geography, this is a bit tricky because um, since these are very expensive machines, there's a lot of lumpiness per year. So what I did, I normalized it. I took the average of the past 3 or 4 years. Um, and most of this geography is based on the headquarters of each of their clients. So as you can see here, Taiwan accounts for 20% of ASML's revenue, but Taiwan, obviously, there's TSMC, South Korea is Samsung, USA is Intel, right? So more than geography, it kind of depends on their clients. And there's just, since there's high customer concentration, um, it's a bit of a tricky one. But the idea here is that they're pretty well diversified. China, which is a big topic here, is also 20%, and that's across various foundries within China, and a good healthy percent of other clients in Europe and Middle East that are starting to buy more and more of these machines. So in general, this is more dependent on the end client of where they're headquartered and where the foundries are, but it provides a bit of a glimpse on their geography exposure. And this kind of graph on the right, the revenue by end consumer. Uh, uh, so the most important chip here, and perhaps taking a step back here, a bit of chips 101 for everyone. So logic chips are the most advanced ones. They are the brains of all electronic devices, while memory chips are more a bit of a wear and tear, and they're used for storing and processing large amounts of data, right? I mean, none is better than the other. They're just kind of like used for different things. And the idea here is that logic is kind of like the more advanced ones and the more niche ones, at least more dense ones that are more tailored for EUV machines, while memory chips are more tailored for DUV machines. So that's an important distinction to make. So you can see this is for ASML's total revenues. They've tilted more toward logic, which makes perfect sense, which obviously is in line with their ramp up of the EUV platform. Red is in there, approximately 25% on average of ASML revenues. And this green one, which is, the most exciting one, the installed base management, which, they're putting the right seeds to develop their service segment in the years to come once they have a more robust installed base of lithography machines. So, in conclusion, historically, ASML has grown revenues by approximately 20% CAGRs in the past 15 years. So, pretty healthy growth. So, let's delve a bit more on the DUV segment. So, these machines are the workhorses of the industry, right? They are used for less complex chips, meaning 10 nanometer resolution and above, which are normally used in the automotive and power industries. They are normally bought by second-tier clients, which include, Micron and SK Hynix, and they're also heavily bought by developing countries such as China. They also serve as business development for EUV as a current DUV client. Uh, if they kind of grow and mature, they would eventually buy an EUV machine to focus on the more smaller, more dense logic chips. And today, it actually DUV still accounts for the majority of ASML's business, as you can see here on the graph. It accounted for 75% of all units sold in 2024 and 41% of the amount sold. Much less in amount because EUV machines are more expensive. But as you can see here, the purple column is DUV, and it continues to be a pretty important business for ASML. So and just to provide some context here, DUV machines have 50% of gross margins. So by itself, it's a very good business. So before I go to the EUV part, which is kind of like what is one of the main thesis parts of this, I'd like to talk about Moore's law and the Raleigh criterion, because this is basically the innovation that ASML is driving in this segment. They've been doing it for 15, 20 years, and it's absolutely amazing. So ASML lithography ensures the continuation of Moore's law. And just to provide a bit of history here regarding Moore's law. So in 1965, Intel co-founder Gordon Moore predicted that the number of transistors in an integrated circuit or chip would double every year for the next decade. In 1975, 10 years later, he revised this prediction to every 2 years. And his prediction has proven to be true. In the years that followed, this exponential growth led to significant increases in computing power and reduction in cost, driving rapid advances in technology and innovation in this semiconductor industry. So ASML has been the key driver of Moore's law in this semiconductor business, and we can see this real time. And the Rayleigh equation, which is this one in the middle, tells us how small we can shrink transistors and print them on a chip. So high level, and for those nerds like me out there, CD is the critical dimension or the level of resolution that the litho system can print, right? And that is a function of K1, which is a factor related to the optical optimizations, which is basically the specialized mirrors inside the machine. And that is multiplied by lambda, the light wavelength, which, as I mentioned, DUV is at 193 nanometers, and for EUV, we'll see in a second, is 13.5. And that's a huge innovation that ASML has driven. And that is divided by the numerical aperture, which says how well the optics gather and focus light. And this is also, again, related to the mirrors. So basically, what ASML is doing is that it's decreasing lambda as much as possible. Right now, they are at 13.5 nanometers, coming from like 300 nanometers 10 years ago, and increase NA as much as possible, which means making mirrors that are larger and that can therefore reflect the light better. And that basically would decrease the resolution level as much as possible. So with this in mind, let me now turn to EUVs, which is the most advanced technology that ASML is pioneering at this moment. So the first EUV was shipped in 2013, so we're now going on 15 or 12 years of this technology. And it's all about affordable shrink, right? So as I said before, ASML was able to lower the light wavelength to 13.5 nanometers to improve the chip printing resolution. Um, and the level of productivity for the advanced chips is at 220 wafers per hour with an uptime of 95%. This is extremely important. These machines, or the clients of ASML, one of their most important metrics is yield, and higher yield is achieved by having the machine on for most of the time. So here with uptime of 95%, this is actually pretty impressive for ASML's clients. And again, EUV is mostly used for logic chips, but there's also plans for DRAM, which are memory chips, to be using EUV as well. So in essence, EUV is better than DUV and alternatives because you have higher resolution and better overlay performance, which means more alignment accuracy for all the additional layers of the transistors. So here I wanted to put a picture of an EUV machine. As you can see here, the two humans are on the bottom left. You can see the scale of this machine. It literally takes around 12 to 18 months to, to ship the machine from ASML headquarters in the Netherlands to the foundry's on-site location, whether it's the US or Taiwan or wherever. So there's a huge amount of logistics, disassembling and reassembling that goes into place to put this on one of clients' foundries. So again, ASML has been building the most advanced chip making machine in the world. And the holy grail, as we all know, for this type of business model is the installed base management, right? ASML has been able to develop this feedback loop for its own machines. It sells a process control software which has 70% gross margins. They've also developed an e-beam metrology and inspection system that helps identify defects and corrects them automatically while the machine is on. Like you don't have to turn off the machine to correct the errors. This software corrects it real time while the machine is on. It helps maintain optimal operation and therefore maximize yield. And as an example of this, it enables chip makers to measure the printed patterns on wafers, ensuring that they align with the original design. So this saves time, this lowers waste, and basically helps ASML's clients to increase yield as much as possible. And another important part is that ASML stays connected to all its machines around the world, and which is feeding its internal database every second. So as you can see here on the right, the top green part is the computational lithography, which is the system or the process that goes before or kind of like on a theoretical setting that feeds into the development of the machines themselves. And the bottom blue part, light blue part, is all the processes and uh, metrology and inspection processes that take place that help the machines perform better and feed all the data back to the continued innovation of the machines going forward. So it's definitely a closed loop that uh, makes ASML's machines stay sharp and continue to be the best machines in the industry. And so let's talk about a bit about how ASML is continuing to be the pioneer in this space, because we've already talked about what history ASML's history regarding this, which they've done an incredible job. What happens in the future, right? So ASML continues to invest approximately 25% of total revenues in R&D and CapEx, and that's around 6 billion euros annually. Um, the Hyper NA is currently being developed, which is the latest EUV machine out there. This machine will be bought by the three largest foundries, and this machine is basically for the most dense parts of the chip. And the first Hyper NA is expected to be shipped by 2028. So just to give an idea, the long uh, tenure that it takes, like from R&D investment to actually shipping the machine, it takes approximately 7 to 8 years, as ASML has talked about Hyper NA for the past probably 2 years, and they expect to ship the first one in 2028. And all of this, uh, actually, this is a good parenthesis. All of this is talked with their clients. So they sit down with TSMC several times a year, and they work on the roadmap together. So this is very much in line with each of ASML's clients' needs. And well, new entrants have failed to kind of break ASML's moat, both in terms of new chip making technologies and our regional players. Other technologies to build chips which actually were considered by ASML 20 years ago, have still not been able to debunk lithography and ASML's innovation. And to provide a couple examples, so multi-electron beam is a technology that is not able to scale above 10 wafers per hour. So this is way below the current productivity of more than 220 wafers per hour for an ASML machine. And the other technology, which is has been talked about a lot, is nano imprint lithography. And the problem with this is that with each additional layer of printing, dirt particles accumulate and mess up the wafer. And this is one of the reasons why the EUV machines use a vacuum in their machines in order to avoid all the debris from outside that would decrease the yield of making more chips. And again, in terms of DUV going more to the more basic machines, they compete with Canon and Nikon, but again, they have very low market share in DUV. And another important aspect is China, which has been a regional player that has tried to replicate ASML's innovation, but with no success. And we'll talk about China in a couple more slides. So the conclusion here is a very strong position of ASML in both EUV and DUV technologies, and ASML is not resting on their laurels, and they continue to reinvest back into the business. So moving a bit to management, and what have they been doing with the excess cash flows from this amazing business?